Good morning, children. Welcome to your chemistry online class. I hope all of you are fine. So, let's start today's class.
So, we have discussed so many bond parameters such as bond length, bond order, bond angle, lattice energy, etc. So, if we check the Lewis structure, we can see that in that molecule there are lone pairs of electrons, bond pairs of electrons, central atom, etc. So, if we check the molecule, in order to describe the strength of a bond or stability of a bond, we need to know a new term called resonance. Resonance is the ability of a molecule can exist in different forms. That is, if we take a molecule that is O3, ozone molecule can exist in different form for the stability. So such ability of a molecule is known as resonance, and such structures is known as resonance structure. So if we take the single Lewis structure, it cannot explain the stability. So if they rearrange in that, they will get more stable compound. So you can see here the example of ozone molecule. If we take this ozone molecule, here you can see the structure. Here you can see this oxygen having 1, 2, 3, 4, 4 lone pairs of electron, and this oxygen having 6 lone pairs of electron. While drawing the Lewis structure, we have discussed this. In the same manner, it can exist in the form of like this also, interchange of these two oxygens. So such forms, that is 1 and 2, are known as canonical structure, that is similar structures. So, and it can exist in this form also. So in order to attain the stability, a molecule can exist in different form. This is known as resonance structures. So here you can see OO single bond and double bond. So if we interchange, we'll get another model. So like this method, resonance structures can show. For example, another example, the resonance structure of carbonate ion. Here you can see the carbonate ion can exist in different forms. Maybe the double bond here, or different form it can exist. It is forming by the shifting of lone pairs of electrons. If you check here the if the bond shift here, by the shifting of lone pair of electron, this bond will forming, this structure is forming. If you check here, if the bond shifted here, it can, if you check here, this lone pair of electron shifted here, we'll get this form. If the lone pairs of electron shifted here, we'll get this form. Similarly, these are the canonical structure. This is occurring due to the movement of lone pairs of electrons or negative charges. Then here you can see another resonance structure of our carbon dioxide molecule. Any type of structure is possible. So here you can see carbon double bond structure is there, carbon triple bond is there. Here we can see different resonance structures. So why the compounds will undergo resonance? It is for the stability. Resonance stabilizes the molecule. So because the energy of the resonance hybrid is less compared to the canonical structure. For example, compared to these two, this structure having less energy, a molecule having less energy, which will be more stable. So this is the resonance structure. Then polarity of bonds. What do you mean by polarity? Polar. Polarity means charge. Polar means charge. So if we check the compounds, O2, H2, Cl2, etc. These molecules are formed between homoatoms. Homoatoms means same atom. So we are studied covalent bond. If you take hydrogen, there is two hydrogens are there if oxygen. So the two atoms are similar here. So if the two atoms are similar, the electron pair situated exactly between the identical nuclei. So the electrons are arranged in a systematic manner in that. So equal share of electrons are there. But if we take an heteroatom, for example, hydrogen fluoride. So here we can see hydrogen and fluorine. Compared to hydrogen, fluorine having high electronegativity. So what it will do? What do you mean by electronegativity? Electronegativity is the ability of an atom to attract the shared pair electron towards itself. So if we take hydrogen fluoride, fluorine having high electronegativity compared to hydrogen. So what will do in the bonding shared paired electron, fluorine attract this bonding shared paired electron towards itself. So by attracting this towards itself, there is a polarity will form. That is, it is like partially giving and partially accepting. So what will happen is the hydrogen will get partial positive charge, fluorine will get partial negative charge. This is known as polarity. So there is the formation of polar covalent bond. So this process is known as polarization. As a result of polarization, the molecule possesses the dipole moment. So we can define dipole moment as the product of the magnitude of the charge and the distance between the centers of positive and negative charge. So it is designated by the Greek letter mu. Mathematically, we can represent it as charge into distance of separation. For example, if we check hydrogen fluoride, there are charge into the distance between these two atoms. So dipole moment is a vector quantity because it is dependent upon both magnitude and the distance. So it is a vector quantity. It can represent by the arrow. You can see this arrow. If we see any molecule by showing this arrow, this is denoting dipole moment. So this arrow symbolizes the direction of the shift of the electron density. That is, if we take hydrogen fluoride, the electrons are shifting from hydrogen to fluorine, from here to here. So it is representing that. So if we check polyatomic molecules, the dipole moment not only depend upon the individual dipole moments, also the spatial arrangement where it is in arranged. So if we check here, we have to take the vector sum. Maybe the dipole moment direction will be in this way. So if we take tetraatomic molecule are the molecule which is having 4 atom. For example, BF3. If we take BF3, there are 4 atom. 1 boron atom and 3 fluorine atom. The dipole moment is 0 because if we check BF3 molecule, in BF3 molecule, simultaneously the electron cloud will move towards 3 fluorine atom. So the net dipole moment will be 0 because they are equally distributing. But if we take another molecule like NH3, NF3R, there is different dipole moment because the direction of we know the dipole moment is a vector quantity. So we have to consider the direction. So the direction of the movement of the electron cloud will vary in these cases. Here you can see the image. So if we take the nitrogen also highly electronegative in the nature, so the direction of the dipole moment will be not equal. Here also it is not equal, so it will possess some dipole moment. So I hope you understood what is resonance structure and dipole moment. And one more topic is there that we'll discuss later. Okay, thank you.